Did I actually hit it? I did. All right. I will begin with a word of prayer. Yes, you read my mind. I guess technically I still have... Oh, wait a minute. I can't pray yet. It's not class time. So you guys looking forward to the weekend?
No. Absolutely not.
Oh, that's right. You still have a quiz before the weekend. You're looking forward to the quiz, right? Yeah, okay. I almost forgot about it, but then Nathaniel talked to me about it. That reminded me. So. I'm a bad person. All right, let me begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Again, Lord, we thank you that we can have your righteousness instead of our own if we just accept you, your free gift that you've offered for us. If we accept you into our heart, Lord Jesus, we just thank you for that. And I just pray you guide our thoughts today and help us to just do our best, Lord, for your glory. In my prayer, Lord Jesus. Amen. All right, so I thought it would be fun. We're allowed to have fun, right? To talk about so check this out. If I was to take the determinant of, let's say, E1, E2, and then say A1 and A2, what would that be? I mean, you should say, well, if here E1 and E2 being the unit vectors in R2, I mean, you should be like, that doesn't make sense. We talked about how to take the determinant of a matrix of numbers, but you have vectors in the first row and you've got numbers in the second row. This is not allowed. All right, well, I'm going to ignore you and just pretend it makes sense. A2 E1 minus A1 E2, what is that? In the other notation, that is A2 minus A1. So what's going on here? Yeah. Whatever. Thank you for reminding me. I'll think about it. So if that's the vector, what's this new vector we've created? What's this thing? It's this guy over here, right? If you look at it. N equals 2. N equals 3, you can do this trick. In fact, many of you recall it from calculus 3, right? Right? This is, of course, nothing more than exactly what we defined to be the cross product of A and B. Right? So, I mean, pictorially, it's something like, there's some kind of plane. In that plane, you've got the vectors A and B. And we know what A cross B does. If we've had calculus 3, it gives us a vector which is perpendicular to the plane, right? Now, you could do this for 4 dimensions too, right? You could put E1, E2, E3, 4, and then you could put a triple of 4 vectors as the rows, and then you'd create a 4th vector from the given 3, which is perpendicular to the original 3. So the determinant can be used in this way. But I would say it's not really the determinant. However, check this out. There's a formula like this. A cross B is equal to the sum over I, j, and k of epsilon I, j, k, a sub I, b sub j, e sub k. That formula is not heuristic. It's not an abuse of the determinant notation. That formula is legit. So if you want a careful formulation that's not an abuse of determinants, you use that notation. But it is the determinant. That's the pattern. Yeah. So anyway, just a thought. If we were given a set of n minus 1 vectors in Rn, and we want to create another vector which is perpendicular to those n minus 1 vectors, we could kind of use this trick to create the next vector. Just a fun calculation. Here's an example that maybe is a good test question. I don't know. How about this? Find all v in R3 such that S equals to 1, 2, 3, 1, 0, 1, V is a linearly independent set. Yeah.
That red line you drew up there, that's perpendicular to vector A, right?
Indeed, yes. So what the sort of the two-dimensional, it's not a cross product, but the two-dimensional analog of the cross product is just creates a new vector which is just rotated 90 degrees counterclockwise from what you're given.
Okay.
Yeah. A cross B gives you a vector which is above the plane with A and B as tangents. Okay. So how would you do it? I said all V, right? Not just one. I mean, anybody can pick one. Pretty sure E2, if I took V equals to E2, that would be linearly independent. I don't think there's any way I can just get 0, 1, 0 as a linear combination of 1, 2, 3 and 1, 0, 1. That asymmetry between the 1 and the 3 I can't compensate for with what's given there, you know?
Find everything that makes it dependent. Say it's not those.
Not those. Everything, okay, everything is not. So one thing we can do is we can look at the matrix. So I'm going to say, here's what I'm going to do. I'm going to say let V equal to ABC, right? I think that's probably an important step to make. We can't choose A, B, and C a priori, maybe before the fact. We got to let variables be there. And then our notation that I haven't emphasized enough, but a notation which is nice, is the matrix of the set S is defined to be just the vectors in the set like glued together. Now, admittedly, it doesn't quite make sense because unless the set's an ordered set, maybe that's a little bit sketchy, right? Oh, I don't need these bars in here. I'm just going to write 1, 0, 1, A, B, C, right? This is the matrix of the set, if that makes sense to you. So what did we learn last class? We learned that a square matrix is invertible if and only if it has linearly independent columns, if and only if it has determinant what? Non-zero. What do you want to look at in that list of things I just said? What is computationally easiest to hack through here? Definitely determinant, right? We can calculate the determinant of this. If the determinant is 0, it's linearly dependent, right? So if it's non-zero, it's linearly independent. And there you go. So we calculate the determinant of this matrix. And that's going to give me 1 times 0 minus b minus 1 times 2c minus 3b plus a times 2 minus 0. In other words, the determinant of this set, this matrix, which of course corresponds to, well, anyway, determinant of that matrix is, what do I got? Looks like I've got 2a plus 3b, oh wait a minute, there's another one over there, plus 2b minus 2c, right? So S is linearly independent if and only if the determinant of the matrix formed by forming S is not equal to 0, which is true if and only if 2a plus 2b minus 2c is not equal to 0. So hence V equals to ABC such that, 2a plus 2b minus, oh, this is tacky. Why am I putting the 2? So divide by 2, right? So a plus b minus c not equal to 0. Infinitely many choices. Which is not surprising if you think about it geometrically, right? There's two, there's a plane, right? There's like a plane. In that plane, you got the vectors 1, 2, 3, and I don't know what it looks like exactly, I don't really care, 1, 0, 1. And so as you think about a vector v being linearly dependent, geometrically what that means, right? If v is linearly dependent, it means that v is tangent to that plane, basing all the vectors at the origin. And it seems like the odds of that actually happening are pretty low for a given. If you just pick an arbitrary vector, odds are pretty good in your favor that it's going to be linearly independent. Just looking at it, yeah. And so that's why there are many, many choices. Yeah. Okay. Any questions? So yet another use for determinants. We can determine when a next arbitrary vector is linearly independent. Now, important steps in this solution was doing what? Like this step of saying that the unknown is ABC is so mission critical to our thinking, right? If you don't do that, it's kind of hard to make progress in this level of notation. All right, so this brings us to Cramer's rule. Kramer with a C as opposed to the more popular one with a K. So here's the rule. If AX equals to B is system of n equations and n unknowns such that the determinant of A is not equal to 0, then the solution is given by x1 equal to the determinant of A1 divided by determinant of A, x2 determinant of A2 divided by determinant of A, and so forth and so on. The jth component, it would be the determinant of A sub j divided by determinant of A, where we define A sub j is matrix where the jth column of A is replaced with B. Yes?
Is this supposed to be determinant of A2 over determinant of A for x2?
Yeah, that's a 2. Not a terribly well written 2, but a 2. Now, I mean, I could be more, so A sub j, the definition, let me write it out a different way. Here's the way it works. Column I of A sub j is equal to the following. It's just column I of A for I not equal to j, and it's equal to B if I equals to j. If that still doesn't make sense to you, A1 looks like this. B, and then you got column 2 of A, column n of A, A2, yeah, column 1 of A, and then you got B in the second column, then you got column 3 of A, I hope I have communicated what I mean by A sub j at this point, all right? Now, why is there a solution? So we know there's a solution because we've assumed the determinant is non-zero, right? So what is, if the determinant's non-zero, what do we know? So remark, the determinant of A not equal to 0 implies A inverse exists. Thus, AX equals to B implies A inverse AX equals to A inverse B, which tells me, in fact, that X not only exists, but it is, in fact, given by A inverse B, right? So the solution exists, it's unique, and we can obtain it by multiplying the inhomogeneous term B by the inverse matrix. But what's the catch? What's the catch? I mean, for a given system, what if you don't actually know numerically what A inverse is? Right? Theoretically, this is comfort to us, but pragmatically speaking, actually calculating A inverse is rather laborious, right? So this is a nice theoretical result, but Cramer's rule gives us formulas for the solution. Straight formulas. Let's derive Cramer's rule. So proof of Cramer's rule. Here we go. So we make some observations. First of all, AE1 is column 1 of A, right? Nothing surprising there. AEJ minus 1 is column J minus 1 of A. Right? I mean, there's nothing, this is just basic matrix multiplication stuff. We're assuming that AX equals to B. We're assuming that here X is the solution that we're trying to find a formula for. We know it exists, right? So I'm going to write that right here. In the middle, I write AX equals to B. All right? Then I have AEJ plus 1 equals column J plus 1 of A. And this continues until we get to the nth column. So I'm not really, you're like, what are you doing? I'm just listing things that are true. All right? These are all either immediate observations from matrix multiplication, or they're the assumption that X is a solution. But here's the cool thing, is we now have these n vector equations. They all have the same what? Coefficient matrix. So I can rewrite these as a single equation of the form A times E1, E2, dot, 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 EJ, and then X, EJ plus 1, En, equal to what? Equal to column 1 of A, column 2 of A, J minus 1th column of A, the B, and then column J plus 1 of A, and then finally the, sorry, I ran out of space, nth column of A. What are we looking at? We've got the matrix A. We've got this matrix which is mostly 0, right? This is mostly 0. If we expand this thing, it looks like this. And then eventually there's an X in here. And then finally there's zeros on the last one. Right? What's this over here, though? Right. That is precisely what we define to be A sub j. It's the coefficient matrix with the jth column swapped out for the inhomogeneous term. Now, you can calculate, and I wouldn't say it's immediately obvious, but it's not that hard to show, that the determinant of this matrix is nothing more than xj. I'll do it for a small case so you guys can see it. So like here's n equals 3 case for that, right? You know, I had the determinant of 1, 0, 0, x1, x2, x3, 0, 0, 1. What we could do is we could move the middle column over here. Like that, right? And then we can flip the last two rows Oh yeah, I'm sorry. I'll just, so I get 1 minus from flipping the first two columns. I get another minus from flipping the last two rows, right? And if you think about this, you could do the same thing like generically for x. You could move x over to the first column. That would cost you how many you'd have to go through 1 dot dot dot. You'd get j to move x over to here. It costs you minus 1 to the j, right? But then what you were left with is, you know, you've got, there's somewhere there's like this zeros. There's in the jth row there's zeros. So then below that, you've got the 1, you want to move the 1 up. And like, just if you can just kind of move those up to get the identity matrix in the top right corner. But the thing is, when you do that, you need the same number of row flips as you did column flips. So moving these 1s up will also cost you a minus 1 to the j, I believe. And so in the end, you can generically get something like this. I don't care, whatever it is, stuff in here, jth down here, and the identity matrix up here. and I think I need to be careful. There's some I'm not being careful enough with the plus minuses. Somehow, when you do this, the net number of signs cancels out, and it always leaves you with just xj. I don't know if I've made a terribly convincing case for that, but at least I tried. All right, and that one is x2. Because plus minus plus x2 times the determinant of what remains, which is 1. But generically speaking, that gives you xj. All right, so anyway, what's the point? What is the point? Take the determinant of that equation. So remember that the determinant of a product of two matrices, M and N, is the determinant of M times the determinant of N. All right, that's a property for determinants. And so what we have is the determinant of A, and then I guess I should have given this thing a name, M. Determinant of M equals to, well, the determinant of AJ so this, as I've tried to explain, you can prove is x sub j. I don't think I've quite done that, but you can make that careful. And so solve for it. xj is, the determinant of A sub j divided by determinant of A. And that is Cramer's rule. Any questions? Yep.
So is that whole thing the proof?
Yes. I mean, it's a partial proof. I mean, it's a proof with a jump. The jump is that the determinant of this is x sub j. I think that's the part I've not been as clear as I could in principle be. But yeah, I mean, basically you write down this system of equations, collect it together, take the determinant of both sides. You get determinant A for this, you get x sub j for that. You get the determinant of A sub j over here, solve for x sub j, that's Cramer's rule. Yeah. So an example, suppose we wanted to solve, like, I don't know, ax plus 3 minus b times y equals to 7, and 3x plus y equals to 2. All right. So this is a 3 minus b, 3, 1. That's my coefficient matrix, right? That's my coefficient matrix here. And so A1 is 7, 2, 3 minus B1. My A2 is A3, 3 minus B, 7, 2 for the second column. And so x is equal to the determinant of A1 divided by the determinant of A. Y is equal to the determinant of A2 divided by the determinant of A, which you can see are given by determinant of A1 is 7 minus 2 times 3 minus B. The determinant of A2 is 2A minus 21. And in both cases, the determinant of A itself is just A minus 3 times 3 minus 3B. And there you go. That's the solution. Yep.
I didn't know what order to put like the stuff in for A1 and A2. So like why is 7 and 2
because this is A times xy equals to B, where B is 7, 2. 7, 2 is the inhomogeneous term. The definition of A1 and A2 is that we replace either the first column with B, that's A1, or the second column with B, which is A2.
Okay, yeah, yeah. Thank you.
Mm-hmm. So here, there's another equally valid and fast way to solve this, which is what? Yeah. Oh, that was just head scratching. I think finding REF is going to stump most of you guys. But many of you would have good success with multiplication by the 2 by 2 inverse here. Right, we have a formula for the 2 by 2 inverse. We could write it as a matrix problem, multiply by the 2 by 2 inverse and solve it. That's about as fast as this. Now, of course, there are terms and conditions applied here, right? This calculation is only legit for where the red terms in the denominator are non-zero, right? Which is to say, I can only solve this system if I'm given that this parameter b is not equal to, the a and b are not so situated that a minus 3 times 3 minus b is 0, right? If that's the case, then this is not an invertible matrix, coefficient matrix, and the solution would be, there either would be no solution, there'd be no, I'm not sure. Could there be infinitely many solutions? I think it's just inconsistent in this case, but anyway. Questions? Yeah.
Could you just re-say, what was the other way you could find the determinant of the matrix without doing this? Or
What?
the inverse, sorry.
Oh, the other way to solve this?
What would be the-
Just multiply by A inverse. We can find A inverse here because it's a 2 by 2 matrix, so we know the formula for the 2 by 2 inverse, right? But you know what? With Cramer's rule, we can derive the formula for the n by n inverse, right? I mean, we can do that. Let me show you. Uh-oh, you guys are caught up. Give me a second here, I'll get us booted up. Come on. So if you guys had to guess, what do you think would be on the quiz?
Hopefully just the name and the date.
Name and date. Uh-huh. That's
Well, we'll have to use the encryption.
that would be I guess that would be I guess that
Go to the top.
Will be on the quiz.
Maybe some college level shapes and colors.
college level shapes and colors. Because of graph theory. Yeah, I don't know much about graph theory, so pottery. You guys are weird. It's here. All right.
We'll have a lot of row reduction, that's for sure.
Finally, a relevant comment. Row reduction. Yes, it seems very likely that I would ask you to solve a system of equations by row reduction and or to find the augmented coefficient matrix for a system and solve it, right? Or maybe ask you a question like, here's a set of vectors. Is another vector in the span of this set of vectors? Seems like a very likely question, right? Or how can you choose another vector which is linearly independent if you adjoin it to a given set? Like we did at the start of today, right? Or calculate this determinant. Or what's the definition of linear independence? Stuff like that. In other words, shockingly, the quiz is going to be about things we've discussed in class and or your homework. Probably, will there be a question about wedge products on the quiz?
No, hopefully not.
Oh, I like wedge products though, but no, there would not be. Very unlikely. All right. So here is the proof I just went through. Here is an honest to goodness. You see, this will make you feel better about your life. Look, numbers. Cramer's rule applied to a matrix with only numbers in it. Do you feel better about your day now? See? I can be nice. I mean, there's probably like an arithmetic mistake in this or somewhere, like to make it bad. Let's not look too carefully at this example. Let's just assume it's helpful and go on. All right, find my laser. Yeah, this will work. So, as I was showing you in the example that I just covered up, Cramer's rule is very, very useful for theoretical linear systems, which for some reason we know have invertible coefficient matrix. In differential equations, you study systems of differential equations. You can write it in vector form like that. And it turns out that you can use what's called variation of parameters. In the process of doing that, you end up with getting n equations and n unknowns for the derivatives of this vector of variables, which means since you have other reasons to know that the coefficient matrix in question here is invertible, so Cramer's rule finds the solution for you, and that's like how we actually put the formulas together for variation of parameters for the nth order problem. And I guess I'm sorry, I was talking about systems a second. It's for the nth order problem, but anyway, I'm just saying we use Cramer's rule in connection with the nth order variation of parameters problem in differential equations, which I don't teach because it's too hard. In advanced calculus, you might be looking at two equations in how many unknowns? X, Y, Z, W, X, Y, Z, W? 4. Okay, so 2 equations and 4 unknowns, right? So sort of like just generic counting says if you've got a 4-dimensional backdrop and you've got 2 independent conditions, that should describe some sort of like 2-dimensional space, all right? Now, these are nonlinear equations, so it's not just a plane. It could be some kind of like surface. And it turns out you can understand the calculus of such things by taking the total differential of the equations defining the surface, which means you just, like you learned in Calc 3, take total differentials. And then what you would want to do is to solve this 2 equations in 4 differentials for dz and dw. If you can do that, that means that z and w can be written as dependent variables of the remaining variables, which in this case are the other 2, x and y. And so you want to solve this for dz and dw. How do you do that? Well, put all the dx's and dy's on one side and keep all the z's and w's on the other side. And then if you look at it, and this will always happen, you'll have a linear equation in the differentials. So you can rewrite it as a matrix problem. And Cramer's rule tells you that dz is equal to this, and like that. And then when you study advanced calculus, you'll learn that this means the partial derivative of z with respect to x. This is the partial derivative of z with respect to y. But anyway, all I'm trying to get across to you with this example is simply that we use Cramer's rule to solve these sort of symbolic linear problems, because you don't want to do row reduction on this. I mean, you could, but Anyway, so I think I gave you a homework problem that's kind of like this. Don't be scared of it. It's not that bad. So finally, getting back to what I advertised a second ago, the adjoint matrix. What on earth is the adjoint matrix? The adjoint matrix is the matrix of cofactors. You've actually already seen this. The adjoint matrix of ABCD is this guy. So the way the adjoint matrix works is for like the 1, 1 column, I cross out the first column and first row, all right? That puts this, whatever's left is D. All right? This one, I cross out the first row and the second column, what's left is C. Why is there a minus? Because that is in the 1, 2 spot, so I do minus 1 to the 1 plus 2. There's a minus 1 to the 1 plus 1 in front of D, but that's just 1. Down here, there's a minus 1 to the 2 plus 2, which is plus. And so like But you recognize this. This is the thing we use for the 2 by 2 inverse, right? And that's not an accident. In fact, that 2 by 2 inverse formula generalizes like so. Proof, here's the formula. If you have an invertible matrix, then the inverse is actually 1 over the determinant times the transpose of the adjoint. This formula, in fact, even makes sense over a commutative ring with proper interpretation. So the formula, this is the classical formula for the inverse of a matrix. It's pretty robust. Now this proof right here is essentially based on the Laplace expansion by minors. I don't really like this proof. A proof 2 I think is easier to understand, because proof 2 pretty much is just use Cramer's rule. So if you look at trying to find the inverse, what are we trying to do? We're trying to solve this and that all the way down. So to solve any one of those equations, we can use Cramer's rule. And if I look at the solution by Cramer's rule, the jth component of it is in fact C1j divided by a determinant of a, because if we swap out a with, when we swap out the jth column in a for E1, then the determinant of that by expansion on that row is just everything else that remains. So that makes, oh, I buried the lead. The adjoint is a matrix of, it's a matrix, every entry in that matrix is a determinant of the submatrix of everything that's not in that entry. It's very blah. I have an explicit example in just a second. But anyway, it's not hard to understand this if you spend about 5 minutes reading it, and that proves that the formula for the inverse is 1 over the determinant times the adjoint transpose. If you'd like me to talk to you more about it, I can talk to you about it in office hours, but that actually makes sense what's written there. Here's a specific, this might be more meaningful to you at the moment. This is like the one, okay, so technically speaking, I need to add plus or minuses to these in order to get the adjoint. But if you take these and put on like pluses and minuses, then that gives us the adjoint matrix. But these, for 1, 1, we're left with EF, HI, right? 1, 2, we're left with DG, FI, like that. And anyway, here it is in all of its glory. This is the adjoint transpose of a 3 by 3 matrix. This is the analog of the formula you know for 2 by 2 matrix inverse formula. And here's straight up the formula for the inverse of a 3 by 3. Do not use this. Do not memorize. If you memorize this, I kill you. All right. You'd have good company if you did. His name is Min. But now, there are many applications of the determinant. In quantum mechanics, sometimes you want to create a wave function which is completely antisymmetric in the exchange of the particles. And if you take wave functions and slap them in a determinant like this, you create something that's completely antisymmetric amongst the positions of R1 through Rn. This is the sort of thing you want to do to create a wave function for a fermion. This is called a Slater determinant. So that's one application. Another less kind of exotic application is this. This would be a formula where if you had y equal to y1, or if you had y equal to y2, then this determinant would be 0, because you'd have a repeated row. So if you look at it, it's also going to be linear in y, y prime, and y prime prime. So this would define a differential equation, right, which is an equation involving derivatives, which takes y1 and y2 as solutions. So if you want to write down a differential equations which has a pair of functions as a solution, there you go. Any functions you like. Like you want to find a differential equation which has solutions e to the x and sine x, just put e to the x here, put sine x here, take the derivative, take the second derivative, and multiply it out. It'll give you this horrible differential equation which has e to the x and sine x as solutions. It's quite awful. It's not a constant coefficient differential equation, though. There's also something called a Vandermonde determinant. So this is the same principle. If I have a given pair of points, x1, y1, x2, y2, and I write this formula down, what happens is if we put x equal to x1 and y equal to y1, what happens? We got a repeated row. So it's 0. Also, if you look at the formulation of the determinant, it's going to give you something that's linear in x and y, because when you multiply this out, when you multiply a determinant out, think about the formula. It's never the case that an entry in the matrix is like squared or cubed in the formula. It appears at most once, the way the determinant works. So if there's just an x and just a y there, you're going to have coefficients, which are the top 2 rows and the 1. So it's going to be linear in x and y when you expand it out. And so what you have then is an equation that's linear in x and y and is 0 when, and I say linear in the affine sense, right? Not linear in our sense, I'm sorry. Linear as in like we taught you y equals mx plus b is a linear equation, right? I have to unteach that to you. It's actually an affine equation. Linear has a technical meaning we soon learn. Sorry. Anyway, my point to you is this is just a really, well, perhaps at this point in your life, complicated way of writing the equation, 2-point equation of a line. If you wanted the 3-point equation of a plane, just make the matrix bigger and add a z and pick 3 points. I mean, if I had 1, x1, y1, z1, 1, x2, y2, z2, 1, x3, y3, z3, and the last row is 1, x, y, z, that would give me the 3-point formula for a plane. And here's I did row operations to work it out. There it is. We'll come back to this. This last example doesn't make sense yet, but it will later. And you can look at this if you want. Now, so in the remaining 5 minutes of class, I should talk a little bit about one of our major, hey, I said stop. Come on, what are you doing? So I've shown you a lot of things today where the determinant being non-zero was important, right? But think about this. If we had a times x equal to lambda times x, right? Here's a definition. If ax equals to lambda x for some lambda in the field, and x is not equal to 0, then x is eigenvector with eigenvalue lambda. Come on. Stupid thing. So what does that have to do? What does that have to do with determinants? For a given matrix A, what could lambda be? Could it be anything? I mean, how does that work? Well, let's just, take a stab at it. So check this out. Ax minus lambda x equals to 0, right? If and only if what? A minus lambda times the identity matrix times x is equal to 0, right? And so, wait a minute. Think about this. Think about this carefully. If x is an eigenvector, what does that say about this matrix A minus lambda I? It's equal to 0. No. It is not invertible. Right? If that matrix was invertible, I could just multiply both sides by the inverse matrix, and I just have x equal to 0. but we're assuming that there exists an x non-zero, right? So what does that say? That matrix is not invertible. What does that mean? That means the determinant of A minus lambda I has to be equal to what? 0, right? And that, my friends, is the so-called characteristic equation for A. So you take a given matrix, you calculate this so-called characteristic equation. The values of this characteristic, the zeros of the characteristic equation, are the eigenvalues of the matrix. How many are there at most? What kind of equation is that? If A is this, the determinant of A minus lambda I is the determinant of 2 minus lambda 0, 0, 3 minus lambda, which is 2 minus lambda times 3 minus lambda, for example. So for a 2 by 2 matrix, the characteristic equation is quadratic. For a 3 by 3 matrix, the characteristic equation is cubic. For a 4 by 4 matrix, the characteristic equation is quartic. For an n by n equation, n by n matrix, the characteristic equation is nth order. Are there zeros to an nth order polynomial equation? At this point, you should say, I don't know, what's the field? If the field is the reals, the answer is maybe. If the field is complex numbers, the answer is categorically yes. Fundamental theorem of algebra says an nth order polynomial complex equation has n roots, possibly repeated, possibly complex. So anyway, this is a major topic in this course. We're just dipping our feet in the pond here. I'm just trying to tell you determinants play a major role in the discussion of eigenvectors and eigenvalues, which we'll touch much more on later in the course. Oh, and lest I forget, valuable use of class time. Anyway, we're done. See you guys at the, well, so should we have the quiz before or after the questions? What's your preference? Quiz at the start with questions afterwards? I think we should have the quiz at the start.
Then we can ask questions.
So then I can talk about what went wrong on the quiz. And you can ask questions on the basis of that. All right? Yeah. There will, of course, be time pressure. It is a quiz. Was that a...